In this module, which is our last module on fixed income derivatives pricing, we're going to talk about the practice of fixed income derivatives pricing. We'll explain how it is really not much more than using observable liquid security prices to extrapolate and compute the prices of non-observable illiquid security prices. We're going to discuss again the problem of calibration and how it is a difficult problem to solve in practice. So in practice, more complex models than binomial models are used to price fixed income derivatives today. In fact, the models that are used today are a lot more complicated than the binomial models we've seen so far. However, the pricing philosophy is still very much the same. It works as follows. We specify a model under the risk-neutral dynamics, which we're calling Q of theta, and where theta is a vector of parameters that you need to choose. So for example, the thetas could be the AIs and BIs that we have seen in the Holy and Black-Dermond toy models. So we fixed our model. There are some unknown parameters theta. What we will do is we will price all securities within our model using risk-neutral pricing. And if you recall, this is our risk-neutral pricing framework. So what we do is we say that ZT over BT, where ZT is the price of the security in question, BT is the value of the cash account. So that is equal to the expected value, conditional on time t information, under the risk-neutral probabilities of the expected value of the security at time t plus s divided by the cash account, plus all the intermediate coupons or cash flows that you receive between times t plus 1 and t plus s, again divided by the cash account value. This is our risk-neutral pricing framework. We know that there cannot be any arbitrage in the model when we price all of our securities like this. So that's step number 2. Step number 3 is then to choose theta so that the market prices of appropriate liquid securities agree with model prices of those securities. This is the model calibration procedure, and we have seen in the last module some examples of how to do model calibration in the context of the Black-Dermond toy model and when our calibration securities were zero coupon bond prices. The calibration problem typically requires minimizing a sum of squares of the following form. So remember, the theta are the vector of parameters that we want to choose in our model. These could be the AIs or BIs in the Black-Dermond toy or Ho and Lee model. So the goal is to choose the thetas in such a way as to minimize the following. So we have a bunch of securities which are indexing by I here, and we have a market price of the ith security, which is PI market, and then we have our model price of the ith security, PI model, and this model price is calculated using this equation here, equation 14. This is our risk neutral pricing that we use in our model. Doing this ensures that our model prices are arbitrage free. So in our model we can compute this price. We see this in the marketplace, and omega I is a weight. It's a positive weight reflecting the importance of the ith security in our calibration. Maybe omega I is large for some values or for some securities, and omega I is small for other values. Omega I could reflect maybe how certain we are about the market price that we see. Maybe we think this market price is stale, maybe it's a few minutes old, or maybe there's a wide bid-ask on this market price, so we're not as confident of the true value of the ith security. Either way, the omega i's can be used to reflect the importance of the ith security in the calibration. We also have this additional term, which I won't spend too much time on, but theta prev stands for theta of the previous calibration. So the previous model calibration might have occurred the previous day, or the previous hour, or the previous half hour. What we want to do typically is make sure that our calibrated parameters don't move around too much. There are various reasons for this, but it helps to keep the model somewhat stable through time if we penalize theta being too far away from the previously calibrated vector theta. And lambda will be a parameter that's greater than or equal to 0, which reflects the importance of this term to the overall calibration. Once this model has been calibrated, we can use it to hedge and price more exotic or illiquid securities. One problem, however, is that this calibration problem is often very difficult to solve. This is typically a non-convex optimization problem. Well, if you don't know what I mean by non-convex, basically the upshot of that is that there will be many local minima, and it will be very hard to find the true solution to this optimization problem. As market conditions change, we often find that we need to recalibrate frequently, often many times a day. If the model was right, then actually you would only need to calibrate once. So in fact, your model typically in practice is not right. It's never even close to being right. We always need to recalibrate it. So this is very different to the situation in the physical sciences, for example, where typically if you have the right model, then you don't need to recalibrate it very often. In finance, unfortunately, you do. So derivatives pricing in practice then is little more than using observable market prices to interpolate or extrapolate to price non-observable security prices. But risk-neutral pricing at the model level at least implies that we can extrapolate, interpolate in an arbitrage-free manner. And in case you're wondering, we haven't said anything about the true probabilities in this section. We've discussed fixed income derivatives up to now, and we've completely ignored true probabilities. We've only discussed risk-neutral probabilities, Q and 1 minus Q, and in fact in the binomial model we set them equal to a half. So does that mean that derivative prices in practice don't depend on true probabilities? Well, that is not true. Of course they depend in practice, and the dependence actually enters into the calibration process, because the true probabilities will enter into the market's perception of market conditions, economic conditions, political conditions, and so on. And so the market's perception of the true probabilities will certainly enter in here, into the market prices of these securities. So implicitly, when we do this calibration, we're actually including the market's views, the market's probabilities, the market's level of risk aversion into the entire derivatives pricing exercise.